So now we are approaching our last presentation of this CiA Technology Day with special regard to CiA 447. So Mr. Holger Zeltwanger, the Managing Director of CAN Automation Association. Say, Holger, stage is yours.
Welcome from my side to all participants. The last presentation is regarding the future of CAN, and the future of CAN is, as you may know, bright, not only for classical CAN, but also for CAN-AFD. And the third generation of CAN data link protocols is also already under development. This is called CAN-XL, and I will give you a first glance on this new protocol, which will be available mid of the 20th, so that car makers can integrate them in their cars by mid of the 20s. Okay, in general, we have all the CAN standards for the data link layer developed in a way similar to Ethernet. This means we have two sub-layers in the data link layer. One is called the logical link layer, and this acts as a sub-layer to the OSI network layer and the media access control sub-layer, and the MAC sub-layer, the media access control sub-layer, is responsible for moving frames from the LLC sub-layer to the physical signaling sub-layer within the CAN controllers. And of course, there comes the protection of the data into the game by means of stuff bits, CRC fields, etc. You don't need to know all this in detail, because these interfaces between the two data link sublayers, as well as to the interface to the PLS sublayer of the physical layer, which is implemented in the CAN controllers, are normally not accessible. This information is only needed by those who really make this, the chips, who implement this in semiconductors. So you don't care on this, on these interfaces in between the sublayers, but you, as a user, you see the LLC frame format. And we have a new one which covers all three protocols, because it's intended in the CAN data link layer that we can run all three flavors of the CAN data link layer protocols on the same hardware. So we have different fields here, and the green fields which you see, this is what you have to provide as a user of the different CAN data link layers. The gray one, this is added automatically by the LLC sublayer. So for you, what you have to take with you is the green fields are provided by the next higher layer. This could be you if you implement this in devices. And this is then also, if you are receiving these, handed over to your application, and you can see the priority, and you can see which kind of protocols you have selected or which have been selected, and so on. Also, this is mainly just that you know this, and you have to provide this information to the hardware. What is new in CAN-XL? This is that we have separated priority and addressing. In classical CAN, we have the 11 or 29-bit identifier, also in CiA 447, which we use to indicate the priority, as well as the function which we are trying to perform, and the addressing which node has to listen to which frames. So we have now an 11-bit priority ID subfield, and this field just provides the priority assigned by the system designer to this CAN-XL data frame. In addition, you have a 32-bit acceptance field, and this field is included in the 64-bit hardware acceptance field of the CAN-XL controller. So it's very easy and very quick to decide, oh, this frame is for me or it's not for me. And it may contain node addressing information, as you know it from CANopen, that you have the node ID there, and or it indicates the content if it's a PDO or it is something else. You could use a legacy CAN higher layer protocols. In addition, you have the priorities separated from that so that it is much more easy to have more larger complex systems. So for takeaway, in opposite to classical CAN and CANFD, priority and addressing are featured by two different LLC fields in the CANXL frame. So we have also some new features in CANXL, similar to that what Ethernet is providing, so that CANXL can be used as a backbone network for complex network architectures. And now we can combine things better than in the past because we have to hide a lot of this information into the payload, into the data field. And now we have separated fields with that. And these fields are also part of the 64-bit hardware filter. The service data unit type, this is similar what is known in Ethernet as the ether type field. It is so to say, it is an embedded information by the next layer. And you can now indicate that this frame belongs to CANopen, or it belongs to another proprietary protocol or to another standardized protocol. We also can tunnel Ethernet frames if we have also Ethernet networks in our network architecture. And we can tunnel also classical CAN and CANFD frames. We support TCP/IP segmenting, CANopen, CANopenFD, J9039, or manufacturer-specific protocols. As a takeaway, the SDU type is similar to the ether type function, indicating the used next higher layer protocol. And of course, the transmitting node has to provide this information, what next higher layer protocol has been used, so that the receiver can interpret the frame correctly. In addition to this, we also have a virtual CAN ID. This is similar to that what is used in Ethernet as well. We have there the virtual LAN indication, and we have also an 8-bit field and can run up to 256 virtual networks on the same single CANXL network. This enables the implementation of multiple heterogeneous networks determined by the SDU type. This field is, so to say, an embedded layer information as described in ISO 7498-4 from 1998. So this is an old framework already, but still valid and suitable to be used. As a takeaway, CANXL is able to run several logical or virtual networks applications on the same cable using the same SDU type. So you can even run 2 or 3 CANopen networks in parallel, where not all the nodes in the entire network architecture are used for a single virtual network. So with these two new features, the SDU type and the VCID, we have any opportunity we have had also in Ethernet, and this will also be standardized by CiA. To satisfy those people who require security or cybersecurity, we will have an optional data link layer security. And we, in the special interest group of CiA for CANXL, we have established a task force who will discuss an appropriate protocol and specify it for cybersecurity. And the SecBit in the LLC field indicate that you are using this protocol or you are not using this protocol. And we think that the CATSEC protocol will feature a 4-byte header with a cipher control information, the CAN, a secure channel ID, and a freshness value. And there will be also a 16-byte trailer containing the 128-bit authentication tag. For you, as a takeaway, CANXL features optionally a data link layer security protocol, which increases the measures against cyber attacks. Of course, there will be additional measures on other layers, but this is just a hardware layer which now supports auto security. So when we Now looking from the bus side, then we see the MAC frames on the bus running. You see here the protocol data unit, which starts with a start of frame bit. No surprise, we have an arbitration field, which is 15-bit using the priority ID and some additional bits. And those which are in green, they are added by the CAN controller automatically. All the others are coming from the layer above, from the LLC. Then we have the control field. The control field is a longer field than today. We have much more information there. We have some embedded protocol information, as you have seen, the VCID, and we have the STT, which is the SDU type. We have the SEC information. We have the data length code of the following data field, and so on. And we have also embedded the 4-bit to switch between the low speed and the higher speed, and also the DIS field in the acknowledge field, which then informs the transceiver to switch back to the arbitration bitrate. So I can't go in all the details, because if I'm going into the details, then we would need another 2 or 3 hours to describe all the fields. What you need to know is just, this is under development. It has improvements regarding the system design, and we have also security introduced in the data link layer, and we have a payload of up to 2048 bytes. This is a lot. To protect all this and to have the same reliability, and even a better one than with classical CAN and CANFD, we are using 2 CRC fields. We have a 13-bit preamble CRC and a 32-bit frame CRC. The CRC are cascaded. This means the frame CRC protects also the preamble CRC. And both CRCs together are able to detect any 5 randomly distributed bit errors. This corresponds to a Hamming distance of 6. The universities of Stuttgart and Kassel evaluate this reliability, and they double check that we have not overseen any security or any reliability issue. So this means CANXL is really able to detect 5 randomly distributed bit errors in the data frame. Regarding the physical layer, CANXL is very flexible. So we can use, we are using 2 bit rates as in CANFD. Maybe you've heard about that we have the arbitration bit rate and we have the data phase bit rate, and there we can increase the speed when only one node is transmitting some signals. In the arbitration phase, of course, we are limited to 1 megabit per second. And the selected bitrate determine the network lengths. The higher the bitrate, the shorter the possible network lengths, and the other way around. You know this quite well from classical CAN. In the data phase, when only one node is transmitting, the maximum data rate is not limited by the network lengths. It can be 10 megabit and even more. This depends on the transceiver capabilities and the selected other physical components, and of course, the topology which you are using. So CAN XL SIG transceivers, when we specify them, they will be able to transmit and receive edges with frequency up to 10 megabit and maybe a little bit more. The CAN SIG XL transceivers, they are just one option. Other options, you can use standard CAN high-speed transceivers as you know it from the past. You can use them, all of those flavors which are specified in ISO 11898-2. This includes those which with a maximum capability of 1 megabit per second, but also those which have more restrictive parameters, which can support 2 megabit or 5 megabit per second. In addition, CANXL controllers can also run with CAN SIG transceivers. CAN SIG transceivers are those which have a signal improvement circuitry inside, and they are specified in CiA 601-4, and they support bit rates up to 8 megabit per second in bus line topologies and maybe in star topologies with a lower bit rate. For higher bit rates, 10 megabit per second and above, as I mentioned, you need the new CAN-SiC XL transceivers, and they will be specified in this CiA 610 series. These SiC XL transceivers run in 2 modes, slow and fast. In both modes, voltage biasing may be active. In the slow mode, there are dominant and recessive bit, as you know it from classical CAN. In the fast mode, there are level 1 and level 2 signals with different voltage levels than in the slow mode. The CAN-SiC XL transceivers need the support of the medium-independent CAN interface, which is also specified in the CiA 610 series. What is important to know, CAN-XL is scalable regarding the bit time in arbitration and data feeds. It can use different CAN transceiver technologies. Even if you have not high-speed requirements, you can use those transceivers which you are well knowing, and you have all the system design rules applied as in the past. The medium independent CAN interface, MICI, this is the interface between the CAN-SiC XL transceivers and the CAN-XL protocol controllers. It is based on TX-based signal path pulse with modulation signals, and is still under development, and we have not finalized the documents yet, but we are on a good way, and I hope that we will have a stable document by end of this year. So what you need to know, if you want to use these CAN-XL SiC transceivers, then you need CAN controllers with a MICI interface, and then you can connect them. In the CAN-XL and in the OSI layers, you see it's quite clear that you have that what is in dark green colored, this is what is implemented in the CAN controllers, and this is part of the CiA 610-1 document. The CAN-XL SiC transceivers, they will be specified in CiA 610-3. And you see here, you also can use, of course, the older or the legacy transceivers, but then you have the AUI interface, which stands for Attachment Unit Interface, as you know it from CAN and CAN-FD. So all the CAN-XL related specifications will be in the moment in CiA, managed in CiA, and later on we will provide them also to ISO for international standardization. So this shows you an example of an implementation. You have the host or standalone controller for CAN-XL. You have the medium access control sublayer and the physical coding sublayer there. And then you have the TXD and RXD lines. And this is attached to the physical medium attachment sublayer unit. This is normally the transceiver. The transceiver with the system-based chip implementation may contain also some parts of the physical media dependent sublayer. It could be optional common mode jocks, termination network, ESD protection, and so on. But just to show you that we try to make the implementations as easy to understand. So what you can take away, CAN-XL controllers can be linked to all standardized CAN transceiver technologies, providing AUI or MICI interfaces. We also try to harmonize and to standardize higher layer protocols within the CiA organization regarding CAN-XL. Therefore, CiA will specify some SDU types and the corresponding address field usage, e.g. for legacy CAN. We will support the development of an improved ISO 15765-2 transport protocol using the 2048-byte LLC data field. This is already discussed in the corresponding ISO working group. CiA will also specify a multi-PDU concept for homogeneous and heterogeneous application layers so that you can mix in one frame and, for example, a CANopen or CANopen FD message with a J9039 message or with any other kind of messages from other protocols. And CiA will specify also the tunneling of Ethernet frame. This is one of the main purpose of the corresponding task force. So CANXL is designed to support higher layer protocols, including approaches supporting multiple virtual network applications. So this means CANXL is really designed for network system architectures and can be used also as a backbone network. CANFD and CANXL, what are the differences? From my point of view, CANFD substitutes classical CAN in mid-term, especially when bandwidth and payload requirements cannot be satisfied by the classical one. CANFD is real-time capable and designed for such applications. CANXL is suitable for high bandwidth requirements and additional functionality such as virtual networking, multi-protocol support, data link security, etc. This is mainly the purpose of backbone networks. Local real-time network applications are not in the first glance the application field of CANXL. This could be also used for that purpose, but it is mainly intended for more complex system architectures. You see that we have additional fields and, so to say, some overhead. And if you don't need that, I would try to solve my problems with CANFD. So CANFD supersedes classical CAN and is completed by CANXL for complex network applications. So this is my presentation in brief on the next generation of CAN data link layer protocols, and I'm open to your questions. Thank you for listening.
So maybe one from my side. Can you say something with regard to the timeline? When can we expect CANXL in the first series cars?
The timeline is a little bit challenging because the main request at the moment is the Volkswagen Group. And they like to have CANXL running in their cars by mid of the 20s, so in 2025. This means 2 years ahead in 2023. The ECU makers should have some products available so that you can make prototype design for cars in the networks. This means we need 1 year or 1.5 years in advance of that. So this means end of 2021 or beginning of 2022, silicon available. We have not yet seen some silicon, except some ASICs, but we hope that we can make in some progress in the next few months to fix all the open technical issues in the specification so that people can implement this not only in ASICs, but also in microcontrollers and on transceiver chips. And this is a tough schedule. And there are also other parties which are highly interested in that by mid of the 20th to have this in the cars available, maybe first for 1 or 2 networks, but then increasingly.
Okay, thank you, Holger. Okay, so this had been the last presentation. So I thank you very much for attending. I hope the CAN Technology Day had been according to your expectations. So please keep yourself updated on what's going on in the CAN community and in CiA community via our email services or our social media accounts. We try also to keep the community informed via further webinars. We will have 2 further webinars this year. So if you are very interested in Holger's topic with regard to the next generation of CAN, there will be a further webinar on this where Holger reports in more detail. Furthermore, if you're dealing with J9039 or further CAN-based higher layer network protocol used in trucks, for example, so then we will have another webinar this year informing you how everything is going on with regard to CANFD and in conjunction with J9039. I hope we could inform you and we can stay in touch. We would appreciate if we can meet you again on other occasions, maybe once again in person. Unfortunately, due to the situation placed now by coronavirus, we are glad that at least we can stay in touch with you here via this web space. And if you have any questions or want to do some stimulations that we can do some activities in this or that action, then please come to CAN Automation, contact us and inform us. So I wish you much success with your CAN-based project and hope that we meet again another occasion. Thank you very much and goodbye.